Okay, we are in 4.3 going to begin talking about random variables that have consistent relationships between the values that the variable takes on and their associated probability. When that happens, we can use a formula to express the probability distribution. So far, we have expressed the probability distribution in table form mostly, and also we've seen expressing it as a graph or a histogram. So that formula, it just means that there's that consistent relationship between the variable and the probabilities associated with the values. So we can express it as a mathematical equation. There are a lot of random variables that we can write as a formula, and so they have names. We are focused on binomial in this one. In this section, some others that are common are Poisson, exponential, and then uniform and normal. We will look at uniform and normal in the chapters to come as well. So let's take a look at what makes a random variable binomial random variable. First of all, it comes from an experiment that consists of n identical trials. So the same thing is repeated identically n times. Second thing is that for each of those trials, there's only two possible outcomes. And we give those outcomes names, success and failure. Now, those words, that doesn't necessarily mean we're assigning the meaning of success and failure to those two outcomes. That's just the convention of labeling the two outcomes. Third thing is the probability of getting a success on a trial, okay, whichever outcome we're labeling as success, that stays constant from trial to trial. So if you remember back from chapter 3 on probability, if the probability stays consistent of something happening after something else has happened, we call that independent. So the trials are independent. What happens on one trial will not affect the probability of what happens on the next trial. So we call the probability of S, we use lowercase p to stand for that, which is going to imply that the probability of a failure is 1 minus p, and we use a q to label that. All right, so now we get down to the actual random variable. So if we assign a value to the random variable and it counts the number of successes that we have in n trials, that is a binomial random variable. Let's look at some examples and identify whether they're binomial and then identify the different characteristics that they take on. So this first one, we flip a fair coin 5 times in a row, and we're assigning x to be the number of tails that we get in those 5 flips of the coin. This is binomial. And so that means that we can identify what n is, we can identify what a success is, and we can identify what p, the probability of a success is. All right, so n is, or a particular trial is flipping a coin. So we're doing it 5 times, so n is equal to 5. And if we want to identify what the success is, we're always going to look to see what is x counting. Well, x is counting the number of tails. So S, or success, is getting a tail when we flip a coin. And when we want to identify the probability of getting a success, probability of getting tails, all right, that's 1/2 or 0.5. Okay, so yes, that one is a binomial random variable, and we've identified the key characteristics. Let's look at the next one. We roll a die 1 time. X is the number rolled. All right, well, we can identify the values that X is going to possibly equal. 1, 2, 3, 4, 5, 6. Okay. That is the number that is rolled on one trial. And how many is that? It's 6. It's not 2. Remember, each trial on a binomial, for a binomial random variable, it can only result in 2 outcomes. So this one is not a binomial random variable. It has 6 outcomes for one trial. Let's look at the next one. Roll a die 4 times, and let x equal the number of even numbers rolled. Okay, so we're rolling a die again, but we're defining what x is a little bit differently. So if we think of one trial is rolling a die, and the result is that we can get an even number or we can get an odd number. So those two things can happen. Those are the two outcomes that we're interested in. So yes, this is a binomial random variable. Number of trials, n is 4. A success is getting an even number. And the probability of a success is, we have 3 out of 6, or 1/2, or 0.5. Okay, let's look at this next one. Select a marble without replacement from a box of 30 green and 20 blue marbles 5 times. X is the number of green marbles drawn. Okay, so let's kind of go through and just think about identifying the different characteristics. So what would n be here? Well, we select 5 marbles, so we were repeating that trial of selecting a marble 5 times. And the success is the number of green, or is the success is getting a green marble, okay? Because that's what we're saying x is counting. Okay, now, so we've identified those two things. The next thing to think about, what is the probability of success? Well, the first time around, it's going to be 30 over the total number, which is 50, or 3/5. Okay, now we have to think, what's the probability for the second marble? All right, so let's call this first one P1, we'll call this P2. If we draw green from the first time, well, the numerator is going to change, it's 29, and the denominator is going to change, it's only 49. Okay, these are not equal. So we don't have that characteristic listed up there in number 3. We do not have independent trials, because what happens in one trial is going to affect what happens in the next trial. So this is not a binomial random variable. Even though we were able to identify the n, the success, because those probabilities don't stay the same from trial to trial, this is not a binomial random variable. Okay, so the binomial random variable counts the number of successes in n trials. So let's just define a few more things specifically. We've got n is the number of trials, p is the probability of success on a single trial, q is the probability of a failure. And we can get that by subtracting p from 1. Now we've got sort of a convention of how we identify a random variable. So we've got x is, the random variable. And then we identify what kind of random variable it is with an uppercase letter. So we've got that uppercase B for binomial. And then the two things that are going to uniquely define a binomial random variable are n, the number of trials, and p, the probability of success. So those are the two things that uniquely define a binomial random variable and distinguish one from another. Okay, we're going to have different probabilities when we have different values in there for n and for p. Okay, we looked at expected value and standard deviation for discrete random variables. Turns out we have a really simple way to calculate both of those for a binomial. So these only work for binomial. So for the mean, it is just we multiply n times p. Pretty straightforward. And for the standard deviation, we take the square root of n times p times q. So remember that. So you don't have to multiply the values of x times the probabilities and sum them up when we're looking for expected value for a binomial. So let's look at some examples and just identify the different characteristics of these binomials. The studies have shown that about 41% of adult workers have a high school diploma but do not pursue any further education. 20 adult workers are randomly selected. We are interested in those with just a high school diploma. All right, so here we've got a sample survey sort of scenario where, we're looking at that experiment in terms of kind of what we do in statistics, where we take a sample and take a survey. Okay, so it says that we are interested in those with just a high school diploma. So if we want to identify what the success is here, it would be you ask an individual and they respond that they have just a high school diploma. And the failure is it's not just that. Okay, so let's define the random variable. All right, well, it is going to count the number of the 41, or I'm sorry, of the 20 with just a high school diploma. All right, I'm going to abbreviate that. And it can equal any value, any integer, 0 up to 20. Okay, now let's look at n here is the sample size. We're thinking about each of those 20 people that we ask is a trial of this experiment. Okay, so if we ask 20 people, we've got 20 trials. So our n is 20. And the probability of success, p, is 0.41. Okay, we get that from that 41%. And q, the probability of failure, is 1 minus that. So we get 0.59. Okay, we can now define this random variable using this sort of shorthand notation. So the random variable is binomial, so we use that uppercase B. N is 20, and P is 0.41. Now, this is important because this really is all we need to know to be able to calculate the mean and standard deviation, and what we need to know to calculate probabilities, which we'll get to. All right, so let's find the mean and standard deviation. So that mean is, we're going to multiply n times p, so it is 20 times 0.41. And it's simple as that. Okay, and that gives us a mean of 8.2. All right, so 8.2 adult workers. So I'll just say 8.2 adults. All right, then standard deviation. All right, we're going to take the square root of 20 times 0.41 times 0.59. So that is the square root of, underneath the square root we have 4.838, which if we take that square root and round to 2 decimal places, we're going to get 2.2. Okay. Now, here's the kind of question that we're going to want to answer now. Probability that exactly 15 adult workers have only a high school diploma. So we are looking for the probability that X is equal to 15. Okay, we do not know this yet, so this is what we are wanting to figure out. So to do that, we're going to look at another example, and then we're going to go through the process of kind of deriving that formula. So let's look at another example where we identify these characteristics. About 60% of physical therapy patients with low back pain complete their recommended exercises each week. Suppose 500 physical therapy patients with low back pain are randomly selected. Determine the following. Okay, so we can choose what we want to be the success here. We can choose that they do the exercises to be the success. And then the failure is no exercise. No exercises. All right, so X then is going to be the number that do the exercises. And it can take on any value from 0 up to 500. So 500, it's the number of people that are selected. All right, we can think of each one of those as a trial. So n is 500. And the probability of success if they do their exercises is that 0.6. And so that means the probability of failure, Q, is 0.4. Okay, so if we write down this random variable, it's binomial, n is 500 and p is 0.6. All right, calculating the mean. All right, we're going to take 500 times 0.6. All right, so we're going to get a mean of 300. So if we do this over and over, we can expect 300 of the 500 are going to report that they do the exercises. All right, standard deviation. 500 times 0.6 times 0.4. So we get the square root of 120, which if we round to one decimal place, that rounds to 11. Okay, now we're going to be wanting to answer probability questions. Something like this. What is the probability that less than 300 physical therapy patients do their exercises? So probability that X is less than 300. Okay, so we need to figure out how we find these probabilities for a binomial random variable. All right, so we're going to start off by looking at another example, and we're going to use that to derive the formula. About 20% of high school athletes have a concussion during a season. Randomly select 4 high school athletes and ask if they experienced a concussion. Let X equal the number that report they had a concussion. So let's say that, well, so X is the number that report they had a concussion. So X is counting the success. So that is having a concussion. And a failure then is no concussion. Here's an example where it might seem a little bit of a mismatch to say success is having a concussion. My son had a concussion last winter, and he still is complaining about it. So not usually considered a success. All right, to find the random variable, what does it count and what values does it take on? Well, it counts the number that had a concussion, and it can take on the values 0, 1, 2, 3, 4. N is 4, P is 0.2, and then Q is 1 minus that, so 0.8. The the distribution is binomial with N equal to 4 and P equal to 2. All right, so all we're doing is filling in N and P there. All right, the mean. All right, we're going to take 4 times 0.2, which gives us 0.8. And the standard deviation, that's a square root of 4 times 0.2 times 0.8. Where if we round that, it just comes out to a nice 0.8. All right, so we actually get 0.8 for the mean and the standard deviation. Okay, now we want to build a PDF table, and we don't normally have to do this, but it's going to help us come up with the formula. So first thing, in a PDF table, we want to list the values that X can equal. So we've got a column for that, and then we notice we have the column for the probability. We have a couple other columns that are going to help us get there. So the values that X can take on are 0, 1, 2, 3, and 4. And the number of outcomes is how many outcomes result in that value for X. Now, if you watch the combinations video, we actually already went through this, and we used this combinations function. Hopefully you found that on your calculator, or you can use the one that's posted on Foxtail. But we already calculated these, so the number of ways that we can get 0 having a concussion is just 1. And the number of ways that just 1 can have a concussion is 4. And the number of ways 2 can have a concussion is 6. And then for x equal to 3, it's 4 possible ways. And then for all 4, there's just 1 way. Okay, so again, if you aren't getting where that's coming from, go back and watch that combinations video, and that'll explain where those numbers are coming from. Okay, so now let's look at this next column. We've identified how many outcomes result in that value of x. Now let's look at the probability of one of those outcomes happening for each value of x. So how does x equal 0? Well, that would be if none of those athletes have had a concussion. Okay, so that would be that the first one would say no concussion, the next one, and the next one, and the next one. You notice I'm combining those things with that word and. So if we go back to our probability chapter, that and rule, we multiply when we combine outcomes with and. And when we have independent outcomes, independent events, right? It is just the probability. We don't have any conditional probabilities that we have to think about. So the probability of getting an athlete that says they haven't had a concussion, when we ask one, is 0.8. And then the second one is also 0.8. And then the third one and the fourth one. Well, we have a simpler way to write that. When we multiply 8 by itself 4 times, we can just write 8 to the 4th. Okay, now let's think about x equal to 1. We want to think of just one of those possible ways out of the 4. Okay, well, there's a probability one of them has had a concussion, so that probability is 0.2. And then the next 3 will not have had a concussion. So that's 0.8 times itself 3 times. We get 0.2, or the probability of success times the probability of failure to the third. All right, let's look at the next one. All right, here we've got 2 successes, 2 with concussions. So that's going to be probability of 0.2 times probability of 0.2, so 0.2 squared. And then the other 2 have probability of 0.8. Okay, so for x equal to 3, all right, 3 successes or 3 concussions, it's going to be 0.2 times itself 3 times, so 0.2 to the third, and then 0.8. So 0.8 to the 1. All right, and then finally, for all 4 to have had a concussion, all right, that's going to happen with probability of 0.2 to the 4. Right, and no 0.8s at all. Okay, so that gives us probabilities of a single outcome. For x equal to 0, there only is one outcome, so that actually is the probability. So if we just take 1 times that 0.8 to the 4, that gives us the probability that x is equal to 0, or 0.4096. Okay, so for x equal to 1, there's 4 different ways that we can have one athlete respond that they have a concussion. So it's either the first one, or the second one, or the third one, or the fourth one. We're combining those with or, so that means we're going to add those probabilities. Or we can just take that one probability that we came up with and just repeat it 4 times, multiply it by 4. So it's 4 times 0.2 times 0.8 to the third. Yeah, it turns out that gives us probability for 1 of 0.4096 as well. Okay, so same thing for x equal to 2. 6 ways that can happen. And so we take that probability of a single outcome and we multiply it by 6. So 0.2 squared times. Okay. That gives us a probability of 0.1536. For x equal to 3, again, 4 ways that can happen. So we multiply that probability of a single outcome times 4. That's going to give us a probability of 0.0256. And finally, for x equal to 4, one way that that can happen, so we just have 1 times 0.2 to the 4th, and that's 0.0016. Okay, now, the point of doing this is to write a formula. So you're probably seeing what the pattern is here. So for each of the probabilities, we've got the value that results from the combination. All right, each of those come from this column, the combination. And they each have the probabilities in there. Okay, so this first one, the 0.2 doesn't show up, but if you kind of remember back to doing algebra and doing exponents, we could include the 0.2 in there. I'm just going to kind of put this up here. If we had an exponent of 0, right? Anything with an exponent of 0 is just 1. All right, so then we can also kind of include down here the 0.8 if we put an exponent of 0. So if we start to build the formula, the probability that x is equal to some value, all right, well, we can see that first of all, the first thing that shows up is that combination. Okay, so in each of the cases where you're starting with 4, and what we plug in for the x is, well, what x is equal to. So if we're wanting to write it in a formula form, we'll just leave it as x. And then when we use it, we plug in whatever value we're looking at. Okay, so then what's the next thing that comes? Well, the next thing is the probability of success, right? That shows up in each of these. Okay, so for this example, our probability of success is 0.2. Now we got to figure out what the exponent is. It's changing as x changes, and not only that, it's actually completely matching up with what x is equal to. So whatever x is, that is the exponent on that probability of success. So we can just plug in an x there. So 0.2 to the x. All right, the next thing that shows up is the 0.8, which that is the probability of failure. All right, and if we want to express the exponent in terms of x, well, the first exponent is 4, okay? The next one is 3, the next one is 2, the next one is 1, the next one is 0. So they're descending, okay? They start off with n, and what is subtracted off is the value of x. Okay, so let's see here. We can actually plug in what n is, right, because it's a 4. And so we can plug that in specifically. So here is the formula that we could use to find probabilities for this particular binomial random variable. So this is assuming we have binomial and we have 4 for n, and our probability of success is 0.2. Okay, it's only going to work for those random variables, and it's only going to work when x is equal to 0, 1, 2, 3, or 4. Okay, let's now generalize the formula so that it'll work with any n. So wherever we have a 4, we want to replace that with n. So if we are looking at the probability of x, we can say it is going to be that combination where whatever n is, we plug that in, and then whatever x it is, we plug that in. All right, so we had 0.2 in there. Well, that was p. That was p, so we'll just replace that with a p, and then we know that we have the exponent of x on there. And then the next piece was q, the probability of failure. And we said that that was n minus x for the exponent. Okay, so this will work for all values of x, starting with 0 up to and including n. All right, we define what each of those pieces are, and just remember that this is going to work for when we have n and p. All right, so let's find some probabilities of another binomial random variable. Is the bottled water you're drinking really purified water? A study of various brands of water found that 30% of water is just tap water packaged in a bottle. Consider a sample of 8 water brands and let X equal the number of these brands that use tap water. Okay, so if we define what we have here, the success is tap water. That's what X is counting. So the failure is not tap water. So X is going to equal, all right, the number that are tap water. And X is going to equal 0, 1, 2, all the way up to 8, the number that are being sampled. So the sample size is 8. Tells us that the probability that we're going to get tap water is 0.3. So the probability it's not tap water is 0.7. So this is binomial. N is 8 and P is 0.3. All right, we can calculate the mean. Multiplying 8 and 0.3, we get 2.4. And the standard deviation, 8 times 0.3 times 0.7. And that gives us approximately 1.3. All right, let's write down the PDF formula for this particular binomial. So first thing is we want to start off with that combination, and we put the n at the top, so that's going to be an 8. And we also always put the x here, okay, because that's going to change based on what probability we want to find. All right, and then we have the probability of success, the 0.3. That exponent is x. And then probability of failure, 0.7, and that exponent is n minus x, so in this case, 8 minus x. Okay, we can now use that formula to calculate this probability. The probability that x is equal to 2, or we can just say probability of 2. We go through, replace x with a 2, so this is going to be that combination of choosing 2 from 8, and then 0.3 squared, and then 0.7 to the 8 minus 2, so 6. So here's where you need to pull out that calculator and use your combinations to come up with what that is, which in this case it's 28. And then 0.3 squared, 1.09, or I'm sorry, just 0.09. And 0.7 to the 6. All right, we get something like 0.117 dot, dot, dot. Now, you don't actually have to write all those out. You can just plug them all in at once. And we get 0.296 dot, 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 or we round to 2 decimal places. We're going to get 0.3. Okay, so 30% chance that 2 out of the 8 sampled bottled waters are actually tap water. 30% chance. Okay, let's practice another one. Find the probability that x is equal to 5. Okay, so just making replacements, plugging in 5 for x. We're going to have 8. Choose 5, and 0.3 to the 5th, and then 0.7 to the 8 minus 5, so that's cubed. All right, so I'll just say if you are practicing this for the combination, what you should get there is 50. Okay, when you plug all of that in, we get 0.0466 dot, 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 which rounding to 2 decimal places is approximately 0.05. Okay, so 5% chance that 5 out of the 8 sampled bottled waters are going to actually be tap water. Okay, let's look at this next one. The probability that x is greater than 0. So it kind of looks like we're going to have to calculate the probability that x is 1 plus the probability that x is 2 plus all the probabilities up to including 8. But we could also use one of our probability rules and recognize that we could start with 1 and subtract the probability of the complement of x greater than 0. So the complement of x greater than 0 is x equal to 0. So that turns out to be only one probability that we have to calculate. So 1 minus the probability of 0 . So we got our combination, and then x is 0, so we've got 0.3 to the 0. Remember, anytime we have something raised to the 0, that's just equals 1. So that 0.3 to the 0 is just 1. And then 0.7 to the 8 minus 0, so to the 8. Okay, so we also talked about in that combinations video that 8 choose 0, there is only one way to do that. So the only thing contributing any value here is the 0.7 to the 8. So we take 0.7 to the 8, we get 0.0576. Subtracting that from 1 and rounding, we get about 0.94. Okay, here's another example. I would suggest you pause, work through this on your own, and then come back and look at the results. Okay, we've got earthquake supplies. It has been estimated that only about 30% of California residents have adequate earthquake supplies. Suppose you randomly survey 11 California residents. We're interested in the number who have adequate earthquake supplies. Okay, so a success here is going to be that a resident has earthquake supplies. Let's fill out the binomial distribution. All right, so we're in this section on binomial, so every single time that first identifier is going to be binomial. So we're going to add other distributions where we might have to think a little bit harder about what goes in there. So right now, it's always just going to be the B for binomial. All right, so if we want to figure out what n is here, we're surveying 11, so that's our n, and the probability of a success that they have earthquake supplies is 0.3. All right, so we can write down the PDF formula. Okay, now just keep in mind that this is only going to work if we've got values of x 0 to 11. All right, is it more likely that none or all of the residents surveyed will have adequate earthquake supplies? So this is going to require us to calculate two probabilities, the probability that x is 0 and the probability that x is equal to 11. So if we plug in a 0, it's going to look like this, but remember that these first two things, when we've got 0, these are just both equal to 1. So the only piece that's going to give us probability is that 0.7 to the 11th. And that is 0.01977. Okay, now I'm going to talk a little bit about rounding with probabilities. So far, we've had probabilities that it's been pretty easy to just round to 2 decimal places, and we can kind of capture what it is. We're going to get into where we have really small probabilities, so we're going to want to start to go out to 4 decimal places. So for this example, we would want 0.0198, okay, going out to 4 decimal places. All right, so now let's look at the probability of 11. So we get 11, choose 11, and then 0.3 to the 11. And then here's where the 0.7, that's going to have an exponent of 0 because we're going 11 minus 11. So here, the 11, remember when we choose the same number that we start off with, that's just a 1. This is also a 1. So it's only coming from the 0.3 to the 11. Okay, so the probability we get here is actually a really small number. All right, we're going to have 5 zeros here, 0.00000, and then 177 ... Okay, so we want to round so that we actually get values. So if we only rounded to 4, we wouldn't get any values. So we want to go out till we get some value. So we could write this as this. Okay, so which is more likely? It's more likely that none of the residents have adequate earthquake supplies. Okay, let's ask this question. How many residents do you expect will have adequate earthquake supplies? Hopefully you're recognizing that word means what we are looking for is the mean, all right, the expected value. So we take n times p, so 11 times 0.3, so we get 3.3 of the residents that are, of the 11 that are asked. And the standard deviation, all right, take this square root, and that's going to give us 1.51. All right, if we round that to 1 decimal place, we get 1.5. Okay, let's look at this next one. What is the probability that at most 2 have adequate earthquake supplies? So here, we're not asking for one value, we're asking for at most 2, which would be x less than or equal to 2. So if we're going to use our formula, we would have to find the probability that x is 0, x is 1, and x is 2. Okay, so it kind of looks like we have to use that formula 3 times, and that would work. And then we would add those 3 things together. But this is what we call a cumulative probability, and it's the probability that x is less than or equal to a set value. And to find that, you add the probabilities up for the values of x less than and equal to that value, just like we did in part E. All right, we're going to actually use an online tool that will give us these probabilities rather than using the formula. So then the piece to figure out is, well, what is the probability that's being asked for exactly? So in part E, it's less than or equal to. So what you're going to want to do is go to Foxtail, find the link to the binomial probability calculator. It's 2 places. It's on this part of the week's Foxtail section, and it's also on the assignment for this section. There's a link there as well. Okay, so using that online tool, binomial calculator, let's find this probability that x is less than or equal to 2. So you'll see there's a place to put in the probability of a success on a single trial. So that's when we'll want to put in that 0.3. And then it asks for the number of trials. All right, those are the only 2 things we need to know to be able to find these probabilities. And then it says, what is the number of successes that we're interested in? Well, we're less than or equal to 2. So 2 is the value that we want to put in there. And then it gives us lots of different possibilities. So we want to pick out the one that matches up. So this one is less than or equal to 2. So we go down to where it gives us that value. And let's round to 4 decimal places. So that's going to be a 0.3127 for that probability. Okay, that makes it easy for us. So you don't have to calculate all those probabilities by hand and add them up. Let's look at this next one. Find the probability that less than or fewer than 6 residents have adequate earthquake supplies. So if we write that in probability notation, this is where x is strictly less than 6. We're not including 6. So using the online tool, plugging in a 6 there, we want to pick out that cumulative probability where it's just strictly less than. All right, so that probability from the online tool is 0.9218 if we round to 4 decimal places. All right, the next one, at most 3. So that probability, that at most is going to mean that x is less than 3, but it can also equal 3. So 3 is the largest value. So, all right, we're just going to go and change that 6 to a 3. And here we want the probability of x less than or equal to 3, so that's going to be 0.5696 if we're rounding to 4 decimal places. All right, let's look at the next one. More than 4 residents have earthquake supplies. So that's the probability that x is greater than 4. So 4 is not included, we just want greater than 4. All right, well, our online calculator gives us that value too, so that's plugging in the 4. Okay, that gives us a probability of 0.2103. Okay, the next one, between 2 and 5 residents have adequate earthquake supplies. So between means that we're not including those two numbers. If we write this in probability notation, x is in between those two values. So 2 is less than x, and x is less than 5. So we're going to write it like that. Now, probability calculator doesn't give us a way to put in two values for x, so we're going to need to figure out a way to use what's given to us. So if we start off with the x less than 5 part, that's something we can get from that probability calculator. Okay, that includes all the values of x less than 5, but we only want the values of x less than 5 that are also greater than 2. So we're going to want to subtract off the probabilities related to the values of x that are 2 or less. So if we write down what that is in probability notation, those are x values less than or equal to 2. And that's a value we can get from the table. So probability that x is less than 5, strictly less than 5, we get 0.7897. Okay, and then plugging in a 2 to the calculator, we're going to want to subtract off the probability that includes 2. So that's going to be 0.3127. So doing that subtraction, we get 0.477. Okay, last example. I suggest you pause and work through this on your own, and then we'll look at it together. All right, we have a student takes a 60-question multiple choice exam but did not study and randomly guesses each answer. Each question has 4 possible choices for the answer. Find the following probabilities. Okay, so before we do that, let's just write out what we've got. X is counting the number that are answered correctly. So X is the number of correct answers. So let's figure out what P is. The probability of getting a correct answer. It says randomly guessing, and there's 4 to choose from. So the probability of getting it correct is 1/4 or 0.25. So this means that our random variable x has that binomial distribution. There are 60 questions, so that's our n, and the probability of success is 0.25. So using the online calculator, we want the probability that the student guesses 20 correctly. Actually, we could also use the formula as well. In fact, let's do that. All right, plugging those values in. All right, we're going to have the combinations of 60 choosing 20, probability of success with exponent of 20, and then probability of failure, 0.75, with exponent of 40. Okay, that probability is rounding to 4 decimal places, 0.0383. Okay, so now let's look at most 20. So that's the probability that x is less than or equal to 20. So here's where that formula is not going to work unless we use it 21 times for all the values equal to 20 and less. So here's where it's very nice and convenient to have the online tool. All right, plug those values in. And we get the probability that x is less than or equal to 20 is 0.9456. Actually make that 0.9458. Okay, the student guesses more than 20 correctly. So if we write that in probability notation, it's x greater than 20. Maybe you also recognize that we could also take it's also the complement of what we just calculated, so we just take 1 minus that. Either way, we're going to get 0.0541. And now let's do this one of probability between. So we want the probability that x is between 15 and 20. So greater than 15, but less than 20. Okay, so we start off with the probability that x is less than 20. And then we have to subtract off the probabilities that we don't want. So we don't want the probabilities where x is less than or equal to 15. So we'll subtract that probability. So the probability that x is less than 20 is 0.9075. And the probability that x is less than or equal to 15 is 0.5688. And doing that subtraction, we get 0.3387. Okay, that is the notes for 4.3. Go ahead and give the assignments a try, and I'll see you next time.